We're now going to do a continuation of some of the activities that we were working on in the in-class activities. In particular, we're going to look at finding closed formulas for recursively defined functions and checking to make sure that they're correct. So first we're going to review what we learned about recursively defined functions in the previous in-class activities, in particular in that last set of problems that I had you look at. And then we're going to show how to verify that a closed formula that you have is correct for a recursively defined function. So one of the things, so let's look at the sequence that we were looking at in the activities. So we had y0 equal to 5, y1 equal to 14, and for n greater than or equal to 2, we had yn equal to 5, yn minus 1, minus 6, yn minus 2. So 2 questions about this sequence. First of all, how do we find a closed formula for the sequence? That is a question for another day, but we're going to do kind of the second part is once we've found a closed formula for the sequence, how do we actually check that it really is the correct formula? So if we found a formula that we think is correct, how do we check that it is definitely correct? So one of the things that we discovered is that for that particular recursively defined sequence, there is exactly one sequence that satisfies the recursive definition. Which means if I happen to find a sequence that satisfies the recursive definition, that's the only possible one it could possibly be. Which means that if you have a closed formula that satisfies the recursive definition, that is going to be a correct formula for that sequence. Alright, so here's the definition. y0 equals 5, y1 equals 14, yn equals 5, yn minus 1, minus 6, yn minus 2, for all n greater than or equal to 2. So suppose we find, I don't know, lying on the street, this closed formula yn equal 2 to the n plus 4 times 3 to the n. We think, what the heck, it might be a closed formula for this particular sequence. How do we check? Is it correct? Well, we got to check 3 things, right? We got to check that it makes sure, I mean, the one grand thing that we have to check is that it satisfies our recursive formula. But that in itself has 3 little subtasks. So for instance, we have to check that y0 equals 5, because that's demanded by the sequence. We have to check that y1 equals 14, and we have to check that the recursive formula is satisfied for n greater than or equal to 2. In other words, yn equals 5 times yn minus 1 minus 6 times yn minus 2. All 3 of those things have to be satisfied by that closed formula. So there's our closed formula. Let's go ahead and check. With y0, that's not too bad, right? Because all we're doing there is plugging in n equals 0. And that's an easy thing to do. Let me see. We get y0 equals 2 to the 0 plus 4 times 3 to the 0. 2 to the 0 and 3 to the 0 are both 1. So we get 1 plus 4 times 1. That's easy to compute. That's equal to 5. And that's what we wanted it to be, right? y0 in our original definition was equal to 5. We plugged in 0. We got 5. So that's consistent. So check. How about y1? Well, it's exactly the same thing. We're just going to plug in n equals 1. Right? And when we do that, we get y1 equals 2 to the 1 plus 4 times 3 to the 1. 2 to the 1 equals 2. 3 to the 1 equals 3. You get 2 plus 4 times 3. 2 plus 12 equals 14. And guess what? y1 was exactly, or 14 was exactly what y1 was when we defined it, the recursive definition. So far we're doing great, and actually it hasn't been a whole lot of work. Well, the next one is going to be a bit of work, right? So we're going to need to verify that for all n greater than or equal to 2, and by the way, that's a lot of terms, right? That's infinitely many terms that we've got to check. We've got to check that yn equals 5 times yn minus 1 minus 6 times yn minus 2. All right, yeah, that is not going to be a whole lot of fun, but what will be helpful to us is if we kind of reinterpret this formula and see what it's telling us sort of in a general way. When I say that yn is equal to 2 to the n plus 4 times 3 to the n, what that formula is really telling me is what if I have any old subscript, that's what n is, right? That subscript on the left side is going to have to show up in the exponent of 2 on the right-hand side, and also that exponent of 3 on the right-hand side, right? So that whatever your subscript is on the left, it's the exponent for the 2 and the exponent for the 3. So for instance, if I want to know what yn minus 1 is, and if you look at the recursive formula I have to verify, yeah, I want to know what yn minus 1 is. That n minus 1 is going to be the exponent for the 2. It's going to be the exponent for the 3. So we have a nice formula for yn minus 1. If I want to know what yn minus 2 is, that n minus 2, that's the subscript, that's going to be the exponent of 2, so 2 to the n minus 2, and the exponent for 3, so 3 to the n minus 2. All right, so there's our closed formula for yn. We want to know if that yn is equal to 5yn minus 1 minus 6yn minus 2. So what we're going to do is we're going to do a little algebraic work on 5yn minus 1 minus 6yn minus 2. And hopefully in the end, we find that it's equal to yn. All right. Well, we're just going to plug in the formulas that we just had on the last slide, right? We plug in yn minus 1 is equal to 2 to the n minus 1 plus 4 times 3 to the n minus 1. We plug in yn minus 2 is equal to 2 to the n minus 2 plus 4 times 3 to the n minus 2. And now it's pretty clear that what we're probably going to want to do is use the distributive property on both of those portions of the formula that have the parentheses. So when we do that, we get 5 times 2 to the n minus 1. Let me see, 5 times 4 is 20, so we get 20 times 3 to the n minus 1. And then for that, for the next set of terms, realize that we're multiplying by a negative 6, so everything's going to change sign. So we get a minus 6 times 2 to the n minus 2, and a minus 24 times 3 to the n minus 2. And that 24, by the way, came from multiplying 6 and 4. All right. Well, at this point, what we'd like to do is combine like terms, but there aren't any. There are some that are close, right? You have a 2 to the n minus 1 and a 2 to the n minus 2. Those are almost like terms. And you have a 3 to the n minus 1 and a 3 to the n minus 2. Those are also almost like terms. So how are we going to combine like terms if we don't have them? Well, we're going to have to make some algebraic adjustments so that some like terms appear. And when I say appear, not just by magic, but by legitimate computations. So for instance, if I'm looking at 2 to the n minus 1 and the 2 to the on the left and the 2 to the n minus 2 on the right, the only real difference between those two is that 2 to the n minus 1 has an extra factor of 2, right? That has n minus 1 factors of 2. The 2 to the n minus 2 has n minus 2 factors of 2. But, I could take that 2 to the n minus 1, sort of separate one of those 2's out to the left, and then after I separate that one out, I have n minus 2 factors of 2 left, so I get that 2 to the n minus 1 is equal to 2 times 2 to the n minus 2. I can play the same game with 3 to the n minus 1, right? That's equal to 3 times 3 to the n minus 2. And then I can take those things and just plug them into the formula, right? 2 to the n minus 1 equals 2 times 2 to the n minus 2. That's what I did in that very first term. And then 3 to the n minus 1 equals 3 times 3 to the n minus 2. That's what I substituted in that second term. All right, so that first one I get 5 times 2 times 2 to the n minus 2. That 5 times 2 is going to give me 10, right? And then I've got 20 times 3 times 3 to the n minus 2. 20 times 3 is equal to 60. And then those last terms are exactly the same. And now I've got like terms, right? So I've got 10 times 2 to the n minus 2, and then a minus 6 times 2 to the n minus 2. When I combine those, 10 minus 6 is 4, so I get 4 times 2 to the n minus 2. And then I have, 60 times 3 to the n minus 2, and a minus 24 times 3 to the n minus 2, and 60 minus 24 is 36, so I end up with 36 times 3 to the n minus 2. So that was pretty nice. Much simpler than what it was at the beginning, right? All right, so here, let's go on to the next slide and sort of summarize what we have. We have the same formula for yn, that's 2 to the n plus 4 times 3 to the n. And now we have a nice formula for 5 times yn minus 1 minus 6 times yn minus 2. That's 4 times 2 to the n minus 2 plus 36 times 3 to the n minus 2. They don't exactly look the same, but they're starting to look a little bit similar, right? And actually, if you look at that 4, right, what is 4? Well, another way of thinking about 4 is 2 times 2, right? And that 36, you could think of that as 4 times 3 times 3. And the nice thing is, now if we plug that 2 times 2 in for 4, and then that 4 times 3 times 3 in for 36, we get 4... First of all, what it was before is 4 times 2 to the n minus 2 plus 36 times 3 to the n minus 2. we're going to plug in 2 times 2 for 4, and 4 times 3 times 3 for 36. And notice that in that first term, if you count all the factors of 2 that are there, you get n minus 2 on the right, plus 2 more on the left. That gives you 2 to the n. And if you count all the factors of 3 in the second term, you get n minus 2 factors of 3 on the right, and then 2 more factors of 3 on the left, and that gives you 3 to the n, and then the 4 that just stays 4. And now look at that, and that's the exact formula for y sub n. So that's equal to y sub n. So we just proved that 5 times yn minus 1 minus 6yn minus 2 is equal to yn. That's our recursive formula. And so we proved our recursive formula works, which was the last thing that we had, and that checks out as well. All right, so I don't have any class activities for this, but expect to get one of these on a homework assignment, right? You're going to get a problem where you're going to have to check a closed formula.